Okay. Randomization tests and Bootstrap. Let's zoom in here. All right. So it suits us to review hypothesis testing from kind of your intro stats class. And yeah, I wrote a bunch of stuff here, but I don't know, maybe I should just do okay. Maybe we'll maybe I'll just write some notes here. Sketchbook gave me such grief this morning, so tried creating a OneNote. So what is this going to be called? Stats 102A. This is summer 2018, week 5, Tuesday. Randomization tests. And Bootstrap. Okay. Let's try this out. Where's my pen? I can't see my cursor. Okay. Okay, so let's stats 10 or intro stats review. Okay, so we said something like we have hypothesis testing. And in the hypothesis testing, you have a null hypothesis, which might be something like mu1 is equal to mu2. Here we are testing to see if two populations have the same mean. Okay. And you know what? I don't know how. Okay. So we're going to testing to see if two populations have the same mean, and so the idea is you have population 1, and over here you have population 2. Okay, and the idea is the populations are too big for us to observe directly. So we work with samples. We work with random samples. Okay, so from population 2, we draw, this is sample. This will be sample 2. Okay, and then from population 1, we draw sample 1. Okay, and sample 1 produces mean 1 and standard deviation 1. Sample 2 produces x bar 2 and standard deviation 2. And based on x1 versus x2, x bar 1 versus x bar 2, we try to answer this question: do the populations have the same mean, right? So based on x bar 1 and x bar 2 and the standard deviations, we want to test the hypothesis that mu1 is equal to mu2. Okay? How does how does that test work? What is the appropriate test to use here, by the way? What do we use? The two-sample what test? T-test, right? So, you know, you're in your intro class, you learned the two-sample t-test, right? And you get, you know, your test statistic is going to be what? X bar 1 minus X bar 2 divided by the standard error. X bar 1 minus X bar 2, and the standard error was the square root of S1 squared over N1 plus S2 squared over N2. Is that familiar? Yeah. Okay. And why are we using a t-test? Why do we call it a t-test? Because we're using the t-distribution, okay? And why do we use the t-distribution? Yeah, okay. I think I heard some bits of correct information there. We don't know the population standard deviation, and the t-distribution resembles the normal distribution, but what's the difference between the t-distribution and the normal distribution? Okay, all right, so so you have the so I'll write recall. So the normal distribution, your z, looks like, it's supposed to look like that, okay? That's much nicer, all right. Normal distribution, if I impose a t-distribution on top of it, what would that look like? Is it taller, shorter, wider, skinnier, fatter, what? It's, so the normal, how do I change my ink pen? Okay, so if the t-distribution would be something like, this is exaggerated, okay? But the t-distribution is wider than the normal. Okay, and we use the t distribution when we do not know the standard deviation of the population. Okay, and so what ends up happening is, so instead of the actual population standard deviation, we use our sample's standard deviation. And it should be samples, plural, samples standard deviations. Okay, so we use our samples standard deviations, okay? But this introduces additional uncertainty, right? This introduces additional uncertainty, so you know, it is compensated by using the t-distribution. Okay, but why would we even use the normal distribution or the t-distribution in the first place? Like, where did this test statistic up here, where did this thing come from?
Math.
Huh?
Math.
From math? Okay. What kind of math?
Statistics.
Statistics math. Okay. Thanks. Yeah.
Like z-scores?
Yeah, okay. All right. And so we are using z-scores, but somewhere in the course we're just like, I've got a mean here, I've got a sample mean here, we're comparing them. Here's this test statistic that came out from somewhere. Do we recall? There's an important theorem, the central limit theorem. And what does the central limit theorem say? So, see, I used to not review this, and then students would ask all of these questions, and I thought, okay, maybe we need to spend some time. Okay, so the central limit theorem, don't worry, and it was a long time ago, but does anyone want to take a stab at it? So there's something called a sampling distribution. Does anyone remember what a sampling distribution is? We're on the track there. Okay, so the central limit theorem states that given any population, okay, the sampling distribution of the sample mean of a random sample, there's like the word sample so many times here, okay? The sampling distribution of the sample mean, so basically of x bar of a random sample will, yeah, we'll just say will follow the normal distribution. As n gets bigger. Okay, this is like loosely stated central limit theorem. Okay, right. So the idea of the sampling distribution, okay, so what is this concept of the sampling distribution? The idea was here you've got a population. Okay, the population has mean mu. Okay, and if we draw from mean mu, we draw sample 1, which produces x bar 1, and then we draw another random sample, sample 2, which produces x bar 2, and then you keep, I lost my pointer here. Sample 3, so on and so forth, each of these producing a different, and if you kind of keep track of all of these, this is going to be the distribution of all the x bars. You'd get something that looks like keep track of all the different x bars that you've observed. This is going to look kind of like the normal distribution, right? This is terrible. Okay. That's what we get. Okay. And then maybe you derive this in stats 100B. Have you guys taken 100B yet? Some of you have. Okay. Well, you guys do this, right? Those of you who did take stats 100B? Okay. So, so we show that it follows the normal distribution. And so now that we know that X bars follow a normal distribution, we can then go back and say, well, if I see this X bar, I can make these assertions about the population. Okay? So basically the central limit theorem in summary says, you know, if the population has mean mu, then a random sample from the population will have mean X bar, which comes from a normal distribution centered at mu. So that's what the central limit theorem will state. And so, you know, using that knowledge, we can now say, we can say, you know, if I observe a sample with mean X bar, I can be confident that mu, I can be like 95% confident that mu is not more than 2 standard errors away, right? Something like that. Okay. And then, you know, we did a bunch more math. We arrive at the test statistic. Does that feel good? Remember this? Okay, great. With randomization tests and bootstrap, we're going for the same thing. We want to do a hypothesis test. This is what we want, okay? But we're not going to rely upon the central limit theorem. We're not going to rely upon the underlying math. We're going to just say, we're going to take the definition of the p-value and translate that into something that we can code up, okay? So randomization tests and bootstrap tests. Okay, so we will not rely on the math behind the central limit theorem. There were limitations with the central limit theorem. Do you remember what they were? Could we just go ahead and use the test statistic and the t-test whenever we wanted? No, there were certain conditions that had to be met. Do you guys remember any of those conditions?
Sample size greater than 30.
So the sample size had to be fairly large, right? So either like we know that the population is normal or at least unimodal and symmetric, and if the population is known to be unimodal and symmetric, then you can get away with smaller samples. But if we know that the population is not unimodal and symmetric, or if we're unsure about the shape of the population, we said, well, we just need to make sure our sample is big enough. Maybe we need a sample of, and then the rule of thumb was 30 or more. But, you know, in extreme cases, samples of 30 still aren't big enough if you have like very skewed distributions and stuff. So if you end up in a situation where you don't know the shape of the population and your sample size is not over 30, or then then you're taking a risk. It's dangerous to use the central limit theorem. So anyway, with the randomization and bootstrap test, we're not relying on the central limit theorem. We're not, so we don't need a sample greater than 30, or need to know that the population is unimodal and symmetric. Okay, so these are not required anymore. Okay, instead, let's we kind of take our definition of the p-value and turn it into something we can test. Okay, so do you recall the definition of the p-value? P-value is a probability. It's the probability of what? The probability of observing a random sample like ours, or something more extreme, if we assume what? If we assume that the null hypothesis were true. So if we assume that the null hypothesis were true, we ask, what is the probability of observing a random sample like ours, or something more extreme? Okay, so our example was maybe our null hypothesis is that mu1 is equal to mu2, and maybe our data ends up with x bar 1 equal to 10 and x bar 2 equal to 12, okay? So if the null hypothesis were true, okay, we would expect populations 1 and 2 to produce random samples with means that are about the same. Right? So if the null hypothesis were true, we would expect our two populations to produce samples with means that are about the same. We get one sample had a mean of 10, the other had a mean of 12, okay? In our data, x bar 1 is 10 and x bar 2 is 12, and they are not the same. Okay, and so the question is, if the null hypothesis were true, what is the probability that we get a difference of 2 points or something more unusual? Were true, what is the probability that a random sample would produce that random samples would produce two sample means with a difference have 2 points or more. Okay. Does that make sense? So that's what the p-value turns into, right? So the p-value is the probability of observing a random sample like ours or something more extreme if we assume that the null hypothesis were true. Okay? And in our case, our null hypothesis is that the two populations have the same mean. Okay? And so our question is, if that were true, if population 1 and population 2 have the same mean, what's the probability that we draw a random sample from population 1 and a random sample from population 2 where the sample difference, the difference between the sample means is 2 points or more? Because that's what happened. That's what happened in our data. In our data, we got 10 and we got 12. So what's the probability that this thing would happen? Okay. And in your Stats 10 class, you use the test statistic T. You would say, okay, well, according to the central limit theorem, the combined, the distribution of the combined populations would have this overall distribution, and therefore we have this probability of getting 2 or something greater. Okay. In a randomization test or bootstrap test, when we say what is the probability that random samples would produce 2 sample means with a difference of 2 points or more, we will literally take a whole bunch of random samples and calculate differences between sample means. So we're going to do this like a million times. We take a million times we take sample 1 and sample 2, and we say, okay, random sample 1 produce this value, random sample 2 produce this value. What is the difference between these two samples? Here's another sample. Random sample 1, random sample 2, what's the difference between these two? And we say, okay, these are all the different sample differences that I got. And now I can ask, what's the probability that they get 2 points or more? We can just see, okay, out of the million samples, how many had differences of 2 or more? And that will be an estimate of that probability. So let me just I'll write that. Okay, so the traditional method, okay, calculate a test statistic T, based on the central limit theorem. Okay, so for a randomization or bootstrap test, these are different things, but the central concept is the same. Okay, for randomization or a bootstrap test, we will take many random samples from the population. We will take many random samples from the population. We will calculate the difference x bar 1 minus x bar 2 for all of the samples. Okay, and then we will see how many, I'm going to call this D. Okay, we'll calculate the difference D equal to x bar 1 minus x bar 2, and we'll see how many of the D's have a difference greater than 2. Okay, and then we'll see, in our estimated p-value will be the proportion of D's will be the number of D's that are greater than 2, okay? I should say number of where the absolute value of the D's are greater than 2 divided by total number of D's. Okay, so rather than relying on the central limit theorem and our understanding of the shapes of distributions to say this is the probability that of getting our test statistic, we are going to do the random sampling ourselves. Is that okay? Yes?
The difference doesn't include like equal to 2. So what if like the difference is 2?
2 exactly?
Yeah.
Yeah, so so technically the underlying distribution according to the central limit theorem is a continuous distribution. So the probability that a test statistic is exactly a particular number, like 2 exactly, 2.000 with an infinite number of zeros, that probability is technically 0, okay? Now in real life, we don't have an infinite number of decimal places and things like that. So, there's the question of, do we use greater than 2 or greater than or equal to 2? I don't know if it makes a huge difference. It shouldn't make a big difference. Okay. Okay. Well, let's do this. So the first thing I'm going to do, this is going to be called a parametric bootstrap test. Okay, in the parametric bootstrap test, we will make assumptions. I mean, this is a little bit dangerous, but we will make assumptions about the, it's called parametric because we'll make assumptions about the parameterization of the populations. Oh dear, something just happened. Parameterizations of the populations. Okay, and this just means we assume the populations have a particular shape, have a particular, we'll say, distribution with, with known parameters. Okay, so we'll just pretend. Okay, so let's pretend here's our data. Well, let's make up a story here. I don't know. Okay. I can't think of anything here. All right. Okay. So you go, where do you guys go grocery shopping? You don't go grocery shopping, right? There's only a Ralph's. There's Ralph's and Whole Foods, right? Those are the two shopping. And Trader Joe's. Oh yes, that's the best. Okay, so we'll say, are the here's our question. Okay, this is a very important question. All right, so are the apples at Trader Joe's bigger than those at Ralph's? I don't know. Huh? What do you guys think? All right, so anyway, So you do your research, right? Somehow you get a random sample from Trader Joe's. All right, here's apples, okay? All right, and these are random. I don't know how you get a random sample from Trader Joe's, but you do, okay? And then you get a random sample. This is like the biggest downfall of all hypothesis tests is like, here's a random sample, which is like, I don't even know how that's possible, but random sample from Ralph's, okay? And there, all right, here's your, these are terrible looking, oh, that's a good looking apple, okay. All right, so there's your random sample from Ralph's, okay? And then, and then you weigh each of these, right? How big's an apple? It's like this big, right? Okay. Let's ask Google. All right. Average weight of an apple.
According to Hypertextbook, apple's weight is dependent upon species, the amount of nutrients it receives, and its size. The average apple is between 70 and 100 grams, or 0.33 pound, or 0.7 in 1 N.
Okay. 1 Newton. Okay. That makes sense. The average apple is 1 Newton. Okay. This is like a mind-blowing experience, right? Because like Newton got hit in the head with an apple. So, I mean, that's the legend, right? Okay, so we will say the average size, all right, we'll say 100 grams, okay? That's like too nice. Okay, and then we'll go over to Ralph's and we'll say Ralph's is 96 grams. Okay, this is our random sample, right? And then we have a standard deviation. We need a sample size. I don't know. What's the standard deviation of these Trader Joe's apples? 9 grams, and we had 8 because that's all we could afford. And I don't know, 12 grams, and we got 8 from Ralph's also. Okay. This is the worst. Okay. So this is our data, and we're going to say, all right, let's do this. All right. So this is the parametric part. Is we now assume, because you got to make some assumptions somewhere, right? Okay. So this is our assumption. These are questionable assumptions, but we're going to assume that these numbers that we got, 109, represent the population of all Trader Joe's apples. Okay, we assume that the population of Trader Joe's apples is normal with mu equal to 100 and standard deviation sigma, why can't I draw sigma? Okay, equal to 9, right? And population of Ralph's apples is normal with mu equal to 96 and standard deviation equal, that looks like a delta, equal to 12. This is what we have. Okay, and so here's our parametric bootstrap test. Okay, so our observed difference between x bar 1 and x bar 2 is 100 minus 96. We observed a difference of 4 grams. Okay, and now we're assuming that these are our populations, right? Okay, let's our hypotheses. What would our hypotheses be? So the null hypothesis is that mean weight of Trader Joe's apples and Ralph's apples are the same, right? Okay, and then the alternative, I think I said, are the apples at Trader Joe's bigger than those of Ralph's, right? So now we're going to say mu1 is greater than mu2. Okay, and so we want to know, I observed a difference of 4 grams, okay? If I draw random samples, oh, I'm so sorry, I messed this up. This is not how we do it. Okay, scratch this line out here. Okay, this is you gotta scratch this out. This is wrong. Okay, so that's the null hypothesis, right? Okay. So under the null hypothesis, mu1 and mu2 are equal. Therefore, we assume that the apples for Trader Joe's and Ralph's are coming from the same, I don't know, the same parent population, okay? So I apologize, I messed this up. Okay, here's our hypotheses, okay? And so for the parametric bootstrap test, we assume the null hypothesis is true, okay? Which basically translates into Trader Joe's apples and Ralph's apples have the same mean. Okay, and so our so we'll say the joint population has mean equal to it would be 100 times 8 plus 96 times 8 divided by 8 plus 8, okay, which ends up being 98, okay, and has standard deviation equal to the square root of 9 squared over 8 plus 12 squared over 8. I apologize. This is so we're combining variances and dividing by the total standard deviation. So yeah, what is this? Of course. Okay, can somebody do this math for me? All right, I'll do it. What is it? Okay, square root of 9 squared over 8 plus 12 squared over 8, 5.303. Okay, so that this is what we have, okay? And so our randomization test will take this. So I'm sorry, for a parametric bootstrap test, is we will take a random sample of 8 from the population and calculate x bar, and then we'll take a random sample of 8 from the population and calculate its x bar. And then we find the difference d. Okay, and then we see how often d is greater than 4, okay, because that was what we observed. Is that okay? So that's what we're going to do. So we're going to just write a blank script here. And okay, so our population. So we'll take we'll call this sample 1. From sample 1, we're going to draw from the random normal. We're going to take 8 values. The mean is 98. Standard deviation is 5.303. Sample 2, our norm, we're going to take 8 values. A mean equal to 98. Standard deviation equal 5.303. Now we're going to take the mean of sample 1 and subtract off the mean of sample 2. We'll store this as our d. Okay, and we get here we get a value of -2. Okay, and we can try this again. And we can see what value of d. Here I get -1. Okay, -1.57. And basically, let's do this 100,000 times, okay, and then we'll say for I in 1 through length of d. Let's just do this over and over and over, okay? Is that all right? So we're going to start off with an empty vector for d, and then we're going to just take a sample from the normal distribution. This will be random sample representing Trader Joe's, and random sample representing Ralph's. Okay, and this is difference between the two. Okay, so let's see what happens. And it's done. Okay, and then let's take a look at the histogram of D. Okay, and so we see most of the time we're getting differences near 0. Sometimes we get bigger differences, sometimes we get smaller differences, right? Okay, and so we want to know how many of these differences are bigger than the difference we observed, right? So we observed a difference of 4. So we're going to just take, we can do D greater than 4, and this will give us a logical vector. So I can just say mean of D greater than 4, and this will coerce everything to 0s and 1s, and this will be the proportion of differences greater than what we observed. So this is effectively a p-value, right? An estimated p-value. Okay. So when we took, when we did this, about 6.5% of our random samples produced values where the difference was 4 points or more. Okay, and so we'd say, you know, we got a random sample where one had a mean of 100 and the other one had a mean of 96, and we want to know, could this have happened? I've been out of battery for a while, I guess. Could this have happened by random chance? And the answer is it can happen by random chance. And in fact, when we did 100,000 simulations, it happened about 6,500 times. Okay? And so, so now we have to kind of answer our hypothesis test question, and we might come to the conclusion that we do not have evidence that that they are different. Okay, so here, let me take a snip of this. Throw this. I don't know. Does this work? Oh, it's kind of small. No, that's not what I wanted. Oh, jeez. All right. Okay. How do I make this bigger? No. Huh? Switch it back to this thing? No? Hang on. All right. To the lasso select?
Oh, yeah.
No. Okay. That's all right. I'll figure this out. You guys want this in there though. All right. Switch back to memory. Insert.
You can just go
Home. Paste the picture. Okay, it's ending up right there. And then I should be able to, right? You'd think. Insert, draw, type. Oh, there we go. Look at that. Okay, now I have little handles. Okay. Thank you for your help. Okay. All right, so anyway, so there you go. And we get, and this is what we get. Okay, so that's a parametric bootstrap test. Does that kind of make sense, how that all worked, the logic and the reasoning behind this? So we're not using any central limit theorem stuff. We're just saying, okay, let's make these assumptions about the population, which I fully admit can be risky, okay, because you're making assumptions about the population, right? And so, yeah, probably parametric bootstrap is not all that popular because people are uncomfortable making such strong assumptions about the population. But there you go. Okay, is that all right? Yes.
So we don't need to use our norm in this case because you just deleted the assumption about to the norm.
No. We are using our norm.
Yes, but if they don't come from normal distribution, they still work.
Yeah. So you have to make some assumption about the population, about what it is, okay? And basically you have to make the assumption about what's true about your population if the null hypothesis were true, right? So here we're assuming that mu1 is equal to mu2, and so because we know mu1 is equal to mu2, we're coming up with this kind of, we're saying the joint population has to have this mean and this standard deviation or something like that, okay?
But this does not necessarily come from a normal distribution.
It doesn't answer, I'm sorry?
It doesn't necessarily to be a normal distribution.
Right. It's risky. There's serious shortcomings of this because here we are assuming that we're assuming that the population has a normal distribution, and that could be a dangerous assumption. Maybe you want to say, I don't want to say that, I want to say that the population has this other distribution, and you can do that as well, okay? But So anyway, that's the parametric bootstrap. And let me just kind of show you the randomization test and the regular old bootstrap, okay? I gotta switch back to drawing mode. Okay, so we've got we'll have the randomization test and the regular bootstrap. And here I have some good slides here. And I guess we can call this non-parametric or regular bootstrap tests. Okay, so here, and then all of these things we're making some kind of assumptions, but let me just talk about some of the differences between the randomization tests and bootstrap, okay? Okay, a randomization test will depend on something called exchangeability, okay? And we'll talk about that in a moment. And so first we have to, I want to spend a little bit of time reviewing some concepts from data collection, okay? And so in your intro stats class, what were kind of the scientific sources of data? Like if we go out and collect data, what are kind of, so you have survey data and what else? Experimental data, right? Okay, and both of those have a source of randomization. What is the source of randomization in the survey data? The people you select for your survey should be randomly selected from the population, right? And then what's the source of randomization in the experiment? The treatments are assigned randomly by the experimenter, right? So they both have sources of randomization, but the randomization is different. One is a random selection process, and the other is a random assignment process. Okay, and those have different implications in terms of what we can do with the data. Okay, and so this is just a brief thing that maybe is a little bit redundant. Okay, but we're going to say suppose how we get the data matters. Okay. And suppose we're doing some, I don't know why this is the example we're using, but suppose a dentist wants to know if a daily dose of 500 milligrams of vitamin C will result in fewer canker sores in the mouth than taking no vitamin C, okay? All right, so here's our first scenario. The dentist working with the local dental society convinces all of the dental patients in town with appointments in the first 2 weeks in December to be subjects of a study. So he says, all right, let's look at who's got appointments in the first 2 weeks of December. And then he divides them into two groups. He say, okay, some of these people, they take vitamin C every day, and these people over here, they do not. Okay, and that's how we split them up. And then we ask them, all right, who's got canker sores, right? And we check their dental records to see who's had canker sores. And then we look at the proportion of those who take vitamin C's that get canker sores and the proportion of those who don't take vitamin C and get canker sores. And then we find out that those two proportions are different. And maybe we do some statistical analysis and they're significantly different. They're not just a little bit different by random chance, but they are significantly different. Okay, what can we conclude from here? Okay, so we say the patients are not a random sample from any population, okay? Because how are they selected? They are dental patients with appointments in the first 2 weeks in December. So that's not random at all. That's just like kind of a convenience sample. I don't know if there's anything that is correlated with when people schedule their dental appointments, but there could be, right? I don't know, maybe whatever, okay? So because of that, we can't take the results of this thing and generalize it to a larger population because the sample we have is not random. Okay, if your sample is not random, your conclusions cannot be generalized to a larger population. Okay. The other part is that the study is observational, which means no random assignment was used, so we cannot make cause and effect conclusions. Okay, so even though we find a relationship between vitamin C and the proportion of canker sores, we cannot then conclude that vitamin C is the reason why people have fewer canker sores. Okay, because there's no random assignment, no causal inference can be made. Okay, so all we can say is just that for these patients, those who take vitamin C's happen to have fewer canker sores than those who didn't. Okay, we don't know why, and we don't know if this result would be consistent with another group. So that's our first example. Okay, scenario 2, we take all those patients with appointments in the first 2 weeks of December to be part of a study. Then we randomly assign people and we say, some of you are going to take vitamin C every day. Some of you are not going to take vitamin C. Then at the end of the study, we take a look at their canker sores and we find there is a difference in the proportions. Okay, so what's the difference here? And what kind of conclusion can we make now? Okay, thank you for your response. So again, we have not a representative sample, so we cannot generalize to a larger group, okay? But what we do have this time was that treatments were randomly assigned, okay? Therefore, we can attribute the difference in canker sore outcome to the difference in the treatments that were assigned. Okay, because we do have random assignment, we can say there is a cause and effect relationship. Okay, and so again, we don't know if this result would be consistent with another random group or another group, but we believe we know why, at least for this group, that the proportion is different. We can come to the conclusion, and maybe we can make some kind of assumption and say, well, maybe these people are representative and therefore it can be generalized. We don't know, okay? All right, over here we have a random sample of dental patients. Okay, so we get a random sample of dental patients. We get them to be part of our study, okay? And then we divide them into those who normally take vitamin C and those who do not, okay? We find there's a difference. So here we have a random sampling and no random assignment, okay? So what can we conclude now? The difference here is that because the patients were randomly selected, we can then generalize or infer that the results observed in this study would be consistent with the population, which would be all the dental patients in the town. Okay? So we selected them as a random sample of dental patients, so this can only be generalized to all dental patients in town, right? Which is not going to be the same as the whole town's population, right? Because only certain people go to the dentist, right? Either those who, generally people who can afford to go to the dentist, right? And and if you're poor and you can't go to the dentist, you will not be part of the study, and there might be, the results will be different for that population, right? So, okay, again, it was observational, no cause and effects treatments, no cause and effect conclusion can be made. We don't know if it's because those who normally take vitamin C on their own have other habits that reduce canker sores or not. We're not sure, okay? So anyway, and then again, we can't conclude for the general population since this was a sample of only dental patients. So if the dental patients in this town are representative of dental patients in general, then we can further expand, who this applies to, okay? Okay, and then lastly, we have the random sample and random assignment, and therefore we can generalize this to the population. We can also draw cause and effect conclusions. Okay? And that's what we have here. Okay? In general, it's difficult. Very rarely will you have a situation where you have both random selection and random assignment. Okay? Because random assignment requires consent of people, right? You cannot just randomly assign a treatment to a person without that person's consent, okay? And so you're always going to have people. You might go through painstaking efforts to get a random sample of people, but as soon as you ask them, do you consent to participate in this study? As soon as one person says no, it's no longer a random sample, right? So you can go through tons of effort to get a random sample, and maybe you did, but as soon as you ask, do you want to participate in the study? And the guy says, no, I don't believe in medicine or whatever, it's no longer random, okay? And so, you know, whatever thing you do, it's no longer random, and you can't generalize it to the general population, okay? So random samples will generally be things where they're like non-invasive things, like asking a question, okay? And even then people will say, no, I don't want to talk to you, right? So you know, true random samples are difficult, okay? And then furthermore, experiments with random samples is like almost impossible, okay? Unless you're like dealing with lab rats, okay, and you're like dealing with animals that, you know, we don't give them human rights and stuff. And so, you know, they don't have the option of consenting or not consenting. They get sacrificed for the cause of science. And we might, and this is also a dangerous thing, is you might say the lab rats I have could be representative of the general population of all lab rats. I don't know how lab animals get tested in the first place. But anyway, it's very rare that you have both random assignment and random treatment, okay? So in general, you'll have one or the other, and the kind of test that you would use in those scenarios would be different, okay? The general premise is this. If you had random assignment, okay, you would do a randomization test. Random assignment is a randomization test. If you had random sampling, you'll do a bootstrap test. Okay, maybe I'll write that down. It appears somewhere in these notes as well. Okay, but in general, okay, if the data has random assignment, we'll probably run out of time to cover everything, but random assignment, then use a randomization test. And if the data has random selection, random sampling, use a bootstrap test. Bootstrap being non-parametric, your regular bootstrap test, not your parametric bootstrap test. Okay, so exchangeability, this is the concept that holds up randomization tests. Exchangeability is the idea that under the null hypothesis, all possible permutations of the data are equally likely, right? So if you think about an experiment where you have random assignment, okay? When we did the random assignment, it just so happened that Alice got put into treatment group A and Bob got put in treatment group B, okay? But it was random assignment, and then, you know, if the experiment had been done on another day and, you know, we flipped the coins again, it's possible that Bob ended up in treatment group A and Alice ended up in treatment group B, okay? And so every possible permutation of who ended up in which treatment group is equally likely under the null hypothesis, okay? Is that when you did the random assignment, it's just as likely that, you know, the groups got mixed up in a different way, and that's this idea of exchangeability, is that that any permutation of the data is exchangeable with any other permutation of the data, and the experiment would have been valid prior to conducting it, right? So, you know, on a practical level, this only happens when we're talking about experiments, okay? And that's what you have, okay? Whereas if you did random sampling, and we say, you know, we're going to separate you based on your habits, okay? We're going to put smokers over here and non-smokers over here. Then if you did it on another day, it's not that the people aren't going to be switching groups, okay? So it's not who ends up in which group is not random, subject to randomness, okay? Who ends up in which group is not exchangeable because that's based on kind of some attribute of the thing and not something that was random. Okay, so that's exchangeability. Okay, Mythbusters yawning. Okay, let's watch a video. And oh, you know what? I have to pause the video here.